Now let's go through the practice problems for predicting branches and exceptions. So the first problem here is about filling the branch delay slot. And we're going to do two things to this code. We're first going to analyze how many no-ops are in it and what percentage of the instructions are no-ops. And then we're going to fix it. We're going to try and fill all the branch delay slots, and then we're going to reanalyze how many no-ops and how many things we have in it. So let's go ahead and take a look at this. So starting off here, what's going on? Well, we've got a loop in here that's going to repeat 10 times. Here's the 10 up here. And we're going to go through this data when we repeat 10 times. Now every time we have to find a special value, here's our special value 34, we're going to do something different. So you can say branch if equals special, we're going to come down here instead of going through here. How many times do we hit special? Well, we've got the special value twice in our data. So if we look at this, if we're not special, we're going to have 3 no-ops. So if we're not special, we go through our loop, we have 1 no-op, another no-op, another no-op, and then we continue. If we are special, we only have 2 no-ops. So we have the first one for special, but then we jump down here and skip that no-op, so then we go to the last no-op. So we'll have 28 no-ops since we know how many times we're going to be special and not special. Now how many instructions do we have? Well, we've got 5 instructions at the top for the initialization, and then if we look at how many instructions we need if we're not special and special, we need 10 and 8. So if we're not special, we need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 instructions. And if we are special, we need 1, 2, 3, 4, 5, 6, 7, 8 instructions. So by knowing that, knowing how many times we're special and not special, we can figure out how many instructions we have total, and we can figure out what the percentage of instructions are that are no-ops. So 28% of our instructions, nearly a third, are no-ops when we execute this code. So can we fill the no-ops with useful instructions? Let's take a look at this. So we might say, hey, I can take this add I and I can move it up here. And I can do that because this is always going to be executed. Right? When continue is done for both special and for not special, so I can just move it up there. So that's fine. Then I might think maybe I can move this loop down here, this add I down after the branch. But I can't do that, and I can't do that because it's generating R2, which is required for the branch. So this might not be the right way to start out here. Let's try something different. Let's try moving this add I up here instead. Now I can do that one earlier because I only need it later when I do the branch. So if I go ahead and move that up there, then maybe I can move something else down to here. So if I move that instruction up here, then I can take this other instruction for the next address, and this I can move into the no-op after the branch because I always execute this regardless of whether I take the branch. Okay, so what about putting something in here? What can we stick up there? So for this place up here, we can take this add for summing the data and we can move this down because we always do this anyways, regardless of the jump continue, so we can put it in the no-op slot there. So there we go. Now we've cleaned this all up, gotten rid of all of our no-ops, so let's count the percentage of no-ops. Well, we go through 10 times, have the special value 2 times, so we've got 0 no-ops if we're not special, 0 no-ops if we are special, so no no-ops. This is great. We can also look at how many instructions we execute in total. We still got the 5 initialization instructions, but now we've reduced the number of instructions we need for each case. So if we're not special, we're going to go through and do 1, 2, 3, 4, 5, 6, 7 instructions. And if we are special, we're going to do 1, 2, 3, 4, 5, 6 instructions. So we can calculate the total number of instructions, and now we're just to 73. So 0% are ops, but we've reduced our code from 101 cycles down to 73 cycles. So the code is 27% faster. So this is great. We went through and got rid of all the no-ops and sped up our code significantly. Let's take a look at what the penalty for mispredicting is. So here's some data on how accurate branch predictors are, and here's some data about how many branches there are in various programs. And I'm going to tell you about a particular processor. It's an Intel Nehalem processor. It has 17 cycle misprediction penalty, and let's assume 1 cycle per instruction. So let's take a look at what happens for iTunes with an always taken predictor and a good 2-bit predictor. So here's our always taken predictor. It's right about 60% of the time, and we can do the calculation. So iTunes has 11.76% branches. The predictor is correct 60% of the time, so it's 40% wrong. And every time it's wrong, we pay 17 cycle overhead. So normally it takes us 1 cycle for each instruction. So this means we're 1.8 times slower using this always taken predictor. Let's compare that up here to a good 2-bit history predictor. So this one's up here, it's like, I don't know, 89%, something like that accurate. So for that, we still have 11.76% branches, but now we're wrong only 11% of the time because we're right 89% of the time. Still costs us 17 cycles every time we're wrong, and 1 cycle for each instruction even when we're right, so this is only a 1.2 times slower, or 20% slowdown. So the branch predictor here makes an enormous difference on the performance of iTunes. For reference, a Pentium 4, which is a pretty old processor, gets between 92 and 98% correct. So we should actually expect higher rates than this over here. This is not a great branch predictor these days. Now let's take a look at different branch predictors, in particular this BTFNT, backwards taken, forward not taken predictor. So we're going to compare them for these different loops, and we assume they start out in this not taken state. So let's take a look at this loop here. We're going to do something 100 million times, and then we're going to branch. So backwards taken, forward not taken. This is always going to predict we go around the loop, so it's going to be wrong one time. The one time when we end the loop and we're done. So it's wrong 1 out of 100 million times. How about a 1-bit predictor? Well, the 1-bit predictor is going to start out thinking we don't take the branch, and it's going to be wrong because we do the first time, and then it's going to predict we do take the branch until the last time when it's going to be wrong because we don't take the branch. So it's wrong the first time and the last time are 2 out of 100 million incorrect predictions. The 2-bit branch predictor is actually worse. It's going to think the first time we don't take it, and the second time it's going to be weakly not taken. It's going to take 3 times through this loop before the 2-bit predictor realizes we're taking the branch, and then it's going to predict incorrectly again when we take the last time and we go out of the branch. So it's going to be wrong 3 out of 100 million times. Now let's take a look at this more complicated loop here. So in this loop here we do 100 million times this loop of 10. So we've got one loop in here we go around 10 times, and this other loop we do 100 million times. So this inner loop we're going to do 10 times 100 million times. So let's take a look at it. So for the backwards taken, forwards not taken, this K predict loop here, we're going to predict right every time except the last time, and this J loop, we're going to predict right every time except the last time. So we predict this wrong once every time we go through it, but we go through it 100 million times. So there are going to be 100 million mispredictions for this, plus 1 misprediction for this, over a total of 1 billion executions. Now with the 1-bit branch predictor, we're going to predict this loop wrong the first time we go into it, and the last time we go out of it. And then we're going to predict it wrong again the first time we go into it because we will have changed our prediction. So this loop here is going to be mispredicted 2 times every time we go through it, and we go through it 100 million times. That's going to be 200 million mispredictions for the inner loop. The outer loop is going to be wrong the first time and the last time, but it'll be right the rest of the time. So that's 200 million times incorrectly for the inner loop, plus 2 times for the outer loop. Finally, for the 2-bit mispredictor, we're going to do even worse. So this one here is going to predict incorrectly when we go around this loop a whole bunch of times. So when we go through here, it's going to predict this loop wrong the first 2 times and then get it right every time except the last time. And in this inner loop here, it's going to predict it wrong the first 2 times, but then get it right every other time except when it exits. So if we look at what happens here, when we first go into this inner loop, we're going to say it's not taken the first time, then we're going to see it was taken, then we're going to say it's weakly not taken the second time, and then we're going to see it's not taken, and then we're going to say it's not taken every time again until we leave. When we leave, we're going to go to weakly taken. That means the next time we come into this loop, we're in weakly taken, and we're going to predict it correctly. So with a 2-bit branch predictor, we're going to make a mistake twice at the beginning and once at the end for every loop, but otherwise we're always going to predict it's either weakly taken or taken. So this branch predictor is actually going to do a little better than the 1-bit branch predictor did. Now let's take a look at how branch predictors work with some histories here. So here's our history. We're going to go not taken, not taken, not taken, taken, not taken, not taken, not taken, and conversely not taken, taken, alternating here. So let's take a look at a 1-bit branch predictor. Here's where we take the branch. So this is going to start off in the state of 0, predicting not taken, and guess what? It was not taken. So the next state's also going to be 0. We're going to keep going through here until we see a branch that was taken. Now we predicted not taken. The branch was taken. It's a 1-bit predictor, so we change it to taken. Okay, now we predicted our next state to taken. So that means the next time we're going to predict taken, but we're wrong because it's not taken. So we change back to not taken. And then we continue predicting not taken, and we continue to be right. So we're right 5 out of 7 times. We messed up here when it switched. For the 2-bit branch predictor, we're going to predict strongly not taken. And then even when it's taken, we're going to change from strongly not taken to weakly not taken, but still a predicted not taken. And this is actually great because then on the next cycle it was not taken and we predicted weakly not taken, so we were correct and we go back to strongly not taken. Let's take a look at this alternating pattern over here. So for the alternating pattern, we start out predicting not taken, and so we're going to have predict not taken, but it was taken. So we were wrong. Now we switch to taken, and we predict taken the next time, but we were wrong, so we switch to not taken. Predict not taken the wrong next time, and we're wrong, and we switch. So this is the worst possible case. We're predicting the wrong one every time, and we alternate back and forth. So we're wrong all the time here. We just happen to be right on the first one. The 2-bit branch predictor does much better. So it goes between strongly not taken and weakly not taken, but it predicts not taken every time, which means it's only wrong half the time as opposed to being wrong pretty much all of the time with the one-bit predictor. Now here's a puzzle with a branch predictor. So here we have two different branch predictors, and you can see how good they are. So here are a bunch of applications, and you can see how accurate those two different branch predictors are. And the question is, how can we combine these in order to get the best of both worlds? And the answer here is, we have different predictors to predict different branches. We can use another predictor to predict which one is right. So a branch predictor. And when we do that, we get much better results. So we've got two branch predictions here. We're going to choose one of them, and we'll have another predictor which predicts which one we should choose. And overall, you get significantly better results by doing this. And this is called a hybrid or tournament predictor, and this is sort of a general idea of the sort of predictors that are used these days.